Hi and welcome to Lesson 5 of DMAD's free series of QGIS from the beginners to intermediates. In today's lesson we're going to be looking at the third part of our coordinates reference system. This is a bit of a longer lecture, but please try and stick with it because it's really important to understand why it is that we're doing what we're doing. Please keep remembering to like, subscribe and most importantly share these videos to help as many people as possible. Thanks.
Hi, welcome back to the third and final part of our Coordinate Reference System or CRS lecture. The objective of today's lesson is to learn about geographic and projected coordinate system and learn more about things that we need to be aware of. So why use coordinate reference systems? Well, coordinate reference systems allow every place on the Earth to be identified by a set of three numbers, which are known as coordinates. And coordinate reference systems can generally be broken down into two categories, which we've already talked about. Geographic coordinate reference systems are systems based in a 3D world. Because our world is roughly spherical, they're generally based around a sphere or around a sphere shape. And then we've got projected coordinate systems, which are sometimes known as Cartesian systems or rectangular coordinate reference systems, which are planar. So they're on generally on a 2D, but they can have a 3D value as well. So geographic coordinate systems. These use lines of latitude and longitude. I'm sure you've heard that expression before. And they normally use a height value to identify a position on Earth. And generally any geographical coordinate system, because it's going to be spherical based, will be able to get a height coordinate as well. So our lines of latitude, these are the ones that run parallel to the equator, and they're actually equally spaced into 90 different parts, running from 0 to 90 in the northern hemisphere and 0 to minus 90 in the southern hemisphere, as you can see on the image on the right hand side. And wherever you are on the planet, there's always 60 nautical miles between our latitude lines. So regardless of whether you're by the equator or right up near the poles, there's always 60 nautical miles between these latitude lines. Lines of longitude begin perpendicular to the equator, as you can see. So they all come out perpendicular to the equator, and then they get closer and closer together until they converge at the poles. And there's 180 degrees both sides of the prime meridian. So the prime meridian, as you can see on the image on the right, is the 0 line, and this runs through Greenwich in the UK. You may have heard of Greenwich Mean Time, which is the time where 0 GMT begins, or we also call it 0 UTC now as well, Universal Time. But that's the same line that the time zones are based on. So we have 180 different non-equally spaced sections. So 180 non-equally spaced sections either side of this line, each of which converges at the poles. At the equator, and only at the equator, so at the 0 line, one division of latitude is equal to one division of longitude. So as you get close to the poles, the division of the lines becomes progressively less and less until they converge, as we said on the last slide, to one single point that you could put your finger on. So far we've referred to these divisions, which were called degrees, but the issue is that you can see that if we look at Africa at the equator, then it falls in between 6 different lines here, which is equivalent to 60 of these divisions, or 60 degrees, and that's just at the equator. which means that if we were to just use degrees, then we could only identify 60 different individual points at the equator, and the distance between each of these points is actually over 1,000 kilometers. So we could only identify points 1,000 kilometers apart. So in reality, if we want our coordinate system to be useful, we have to break these degrees into smaller divisions, and we break these down into units called minutes and break these minutes down into units called seconds. And rather unsurprisingly, just like time, we have 60 minutes in a degree, and then we have 60 seconds in a minute. So that means there's 3,600 degrees, 3,600 seconds in a degree. So we can break that down into 3,600 smaller sections. And at the equator, 1 second of latitude or longitude is equal to approximately 30 meters. And then obviously that decreases as you get further northward. So now on to projected coordinate systems, and we'll start by talking about 2D and 3D reference systems. This is probably going to sound very basic and patronising, but apologies. It's something that needs to be covered because not everyone will have covered it. So with our 2D reference system, we generally have a horizontal axis and the vertical axis. The horizontal axis is generally referred to as the x-axis, whilst the vertical axis is referred to as the y-axis. And if we are to have a point A, we give it a set of coordinates. The first is the x-coordinate, and then the y-coordinate follows it. If we're to move this onto a 3D reference system, then generally we flip the planes. We still have an x-coordinate and a y-coordinate, but now we have a z-coordinate as well, which represents height. And as you can see, with our point A now, we have x-coordinate followed by a y-coordinate followed by a z-coordinate. So projected coordinate reference systems, we're going to talk about the Northern Hemisphere because that's where DMAD's work takes place. And in the Northern Hemisphere, the origins of projected reference systems are generally somewhere along the equator, and the horizontal axis increases as you move east, and the vertical axis increases as you move north. So east is the x-axis, north and the y-axis, and it's actually the opposite way around on a lot of the projected reference systems in the Southern Hemisphere. So the Universal Translocator, or UTM coordinate reference system, is one of the most commonly used coordinate reference systems in the world. And to limit distortion, the world is divided into 60 equal zones. You remember we talked about distortion in the last lecture. And each of these zones is 6 degrees wide in longitude from east to west. And it starts from the international date line. So the international date line is sort of west of Alaska, east of New Zealand, and it's also known as the anti-meridian. So we had the prime meridian, which is through Greenwich in the UK, and the anti-meridian, which is 180 degrees out. And so we have 60 equal zones, which I think I've got a picture of in the next slide. Yeah, so we've got our 60 equal zones running from west to east here, starting at the international date line and continuing across. So you can see that the States is around zone 10 to zone 18, the UK zone 30, Africa, well, South Africa is highlighted here and has zones 33 to 36. Montenegro that we work in is also zone 34, and Turkey is in zone 36 that we work in quite a bit. So I'll let you just look at that for a couple of seconds, but these are the different UTM zones. If you're unsure about what UTM zone you're working in, it's very easy to just simply type into Google or whatever search engine you're using, just saying what UTM zone is Portugal in, for example, and you check a couple of websites because occasionally they are wrong, but you'd find that it's in zone 29, for example. Okay. So, defining northings in the UTM is very easy. Northings range from 0 to 10,000 kilometers in the northern hemisphere, and 10,000 kilometers to 0 kilometers in the southern hemisphere, starting from the equator on both occasions. And you may have noticed that 10,000 kilometers is a very exact measurement. And as an interesting side note, 10,000 kilometers is equal to 1 million meters. And actually, a meter is defined as 1/1,000,000th of the distance between the equator and the poles. So that's quite interesting. So the easting of UTM is a little more complicated, as you can imagine, because we have our convergence. But basically, to try and make sure that there are no negative values, each UTM zone has an arbitrary value of 500 kilometers. So the center of each of the UTM zones, so the center of zone 34 has an arbitrary value of 500 kilometers, the center of zone 7 has the same, and that's just so that the zero value is never inside your UTM zone. So if I'm working in UTM zone 16, then my zero value is going to fall in UTM zone 15, so it's going to fall outside my UTM zone. Obviously, depending on where you are in the world, that value, because the lines converge, that value is going to change as to where your western boundary falls. So even though the zero value always falls into the zone on the west, so the zone on the left hand side of your zone, depending how far north or south you are, then that zero value will fall either closer to your western boundary or further away. So at the equator, where our east to west distance is the largest, because we have no convergence at that point, at the equator, the western boundary has a value of 160 kilometers. So from the center to the western boundary is 340 kilometers. Hopefully everyone followed that maths. 500 minus 160. See, 500 is our central point. Minus 160 is 340 kilometers. So we've got 340 kilometers between our central point and our western boundary. By the time we get to 84 degrees north, then this is just, our western boundary is 465 kilometers. So we've actually only got a distance between our central point and our westerly boundary of 15 kilometers at 84 degrees north. And that's because, as we talked about, as we saw the images, our lines running south to north converge as we get closer to the poles till they get to one point. So we're always going to have a wider boundary on our the further south we go to the equator, or the further north we go if we're in the southern hemisphere until we reach the equator. And the inverse is true as well. As we get further north in the northern hemisphere, the width of our zones is going to get smaller and smaller, and likewise in the southern hemisphere. Okay. So the final thing I wanted to talk about is on-the-fly projection. And as you can imagine, we quite often get different shape files for our different projections. So, for example, we might get a file such as background mapping, nice big file, in World Grid System, so WGS 84 is the latest World Geodetic System, sorry. And we might get something in UTM 34 if we were maybe looking at survey areas in Montenegro. And we have this tool called on-the-fly projection, which is present in QGIS, and that allows us to set a CRS, so it allows us to set a coordinate reference system for our GIS environment. And then all files are imported into our GIS environment, are projected automatically into this CRS, and we can turn that on and off depending on the work we're doing, and I'll show you how to do that in either the next lesson or one of the other lessons. So we've got to the end of our 3 lecture series on the coordinate reference systems. I'm sorry it was pretty heavy going, but I think it's something that's really important for people to understand. A lot of people don't understand it, and it can cause problems. But as I said in the last lesson, especially when you're starting out, you're generally going to be given the projection that you need to work in. So yeah, if you're unsure, then UTM is always a good projection to go for, especially if you need to do anything that's going to involve calculations with area, just because it's measured in meters, so it's much easier to work with. And as I said, you can look up the UTM zone that you're working in very easily on the internet, so that's a good one to work from. I'm just going to finish with a quick summary of what we've learned in the 3 lectures. So the first is that map projections present portions of the Earth in a planar or 2D field of view. So that is that map projections take our spherical Earth and transfer it to a 2D flat piece of paper or computer screen, however you want to view it. There are global projections, but generally these projections are optimized for one area of the world. So a projection for Somalia would have really big distortions by the time we reached Asia or Europe, either in one of the ways that we talked about in the last lecture, so whether that's distance, angular conformity, or area. And I've sort of emphasised that again in the next point. Map projections can never truly represent all aspects of the real Earth. They're always going to result in distortions of angular conformity, distance, or area, and that's purely because the Earth is roughly spherical and we're trying to portray that as a flat piece of paper, so we're never going to be able to represent all 3. We're going to have to always choose to sacrifice one of those, whether that's angular conformity or whether it's distance or area. But we might choose to sacrifice a little bit of distortion in each of those to try and make our overall distortion effect less. So a coordinate reference system alongside the set of coordinates is used to define how a point on a map relates to a real place on the Earth's surface. There are 2 different types of coordinates reference system generally. And these are geographic coordinate systems, so ones on spherical, and projected coordinate systems, which are flat or planar. And finally, on-the-fly projection is a functionality in GIS that allows us to overlay different layers, even if they're projected into different coordinate reference systems. So it's a tool that didn't exist a few years ago, well, didn't exist a decade ago, that just makes everything a lot more simple for us. So I hope that's made more or less sense to you. And yeah, thanks for listening. And if you have any questions, don't hesitate to ask me, and I'll do my best to answer them. Yeah, sorry it's been tough going. We will get back to the practical lessons now. Other than that, thanks. Take care. Bye.